let's move to the next section. So this is basically this we will start from cycle detection, then the form of cycle, which is like how big the cycle is, how big a chain is attached to the any node of that cycle. For example, this 3 is having a chain of size 2, this 4 is having a chain of size 2, this 1 is having a chain of size 1. Okay, inward outward that we will detect. We will go in this era because these are key observations when we are going to advanced topic like strongly connected component, and not just finding the strongly connected component but using it to solve some very advanced problems. Okay, but this will not be overwhelming. I'll try to keep it very simple, no rocket science. Okay, so firstly, just think of if I'm having a graph which is having a cycle, which is our course schedule 2 question was that just can we complete it, and if there is a cycle, obviously we cannot complete those courses, right? How can we do it with depth first search? So this is learning first. We are not reinventing, it's known. So let's just note down some of the things. To detect cycle using depth first search, we use states. So we can call it like so visited we are used to of using, right? Visited array which says true or false, whether that particular vertex is visited or not. In place of true or false, let's just call it we will use 3 states. 0 means not visited yet. 1 means I just added I'm going into it. Like for example, if 1 is popped out or 1 is what I'm exploring, I'm adding all the neighbors of 1, right, into my whichever data structure. Then when I am detecting 2, I will simply say that state of 2 is 1. And when I'm done with that entire, I'll go in depth. So when I explore the entire depth from 1, when I'm coming back, I'll convert that 1 into 2. The state of this particular vertex will become 2 at that time when all the neighbors of this is already I have traveled. So we will keep these 3 states, and that will help us to find out if there is a cycle or not. Okay. We can also call it like visited. Let's not call it time actually. We'll come to the time thing later. For now, let's keep it simple. Okay. Now, if we are going to use the state, now let's see how we will use it. In breadth first search, we were using in degree. Hence, we knew which one is our head, from where to start and all, right? In this case, there is no head. So you can think of anything. So if it is given like you are having a graph where vertices are from 0 to n-1 or 0 to n, you can say I'll do DFS from 0 because that is my starting node, right? So that way you can start from anywhere. So in this one also, let's suppose we will start our depth first search from 1. Okay, this will be something like for every vertex, say I, every vertex I in V. So it should give you 1, 2, 3, 4, 1 by 1. It will come, and you will simply check if visited I, which is visited will be an array, is still 1, that still 0. It means you have never visited this one. Then do a depth first search for I. This is what we will try to do, something like this. Okay, this is just for the example. Now, what we will do here when we are doing this, and why we are basically running a loop on I. If we are starting from one element, obviously we should be able to cover everything, right? But there can be separate components, like we saw in the previous video, that if there is no edge between 4 and 7, then 7 and 8, that will be a subgraph. It will be a separate component. So it's possible that if I explore that one component, another component is not explored. So I'll try to basically do DFS on any of the node of another component again. Okay, perfect. So with that, let's suppose I'll start from the smallest node. I can start from anywhere and the result will be same in terms of it will give us the correct answer. So here we will always start from the smallest node, right? Because it is starting from 1. If it would have started from 0, we would have started from 0. So we are doing depth first search. So what will happen is we'll come to 1. 1 will be passed into our DFS as per this, right? So we'll come to 1. As soon as we will come to 1, the state will be converted to state of 1 will become 1. Like we said, first we are converting it into 1. Now we'll check. We will run a loop on all the neighbors of 1. So there is only one neighbor in this case. We will simply go to, we will call DFS on that neighbor. 1 by 1 all. So we'll call on this one first. As soon as we'll go here, the state of this we will check. State is still 0. Obviously by default, every element wherever state is not written, consider it as 0. So this we will convert to 1. Then we will go to 3. Similarly, state of this will be converted to 1. So we can mark it here actually. Let's suppose this is our visited array, which is having all those 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So what we did so far, 0 was not here, right? So what we did so far, for 1, we marked it as 1. For 2, we marked it as 1. For 3, we marked it as 1. Now moving forward, who is the neighbor of 3? So there is only one neighbor we can go to, which is 4. So 4 will go, it is still 0. Yes, we will mark it as 1. From 4, we are having two options. So let's suppose we are going in option this first, 7. Okay, so we are going into 7. 7 is having a 0 as state, so we will be marking it as 1. Then 7 will go to 8 and we'll mark it as 1. Now from 8, we are not having any vertex to go to. That means that we will come out of that loop, and as soon as we are coming out of that loop, we will mark that particular vertex to completed, which is nothing but that 8 will be marked to as 2. This is done. Now, as you know the basic DFS, we'll come back to the parent of it from recursion, and then that loop is done because there is no other place to go from 7. Hence, we will also come out of the loop from 7, and the state will be converted to from 1 to 2. This is also marked as done. This is done. It will return back to the parent in recursion. So from 4, the first you can say depth is done. Now there is still another neighbor or child from 4 to go. So it will go into the next one. The DFS will be called for 5. State of 5 is 0. Hence it will be changed to 1. From 5, we are having one neighbor, which is 1. So we will go to 1. So we are calling DFS. We are calling DFS with 1. When we will come here, we will check that 1 is already in state 1. Neither 2 means it was not completed, nor 0. It's 1. That means we started this depth first search from this element, and we came back to the same element. If we came back to the same element, means the state of the element is 1, and we are visiting that element, that means there is a cycle. So that is going to be our condition. This is what we were trying to establish. If I have to write it down, what I am trying to say, a pseudocode, that you will call depth first search with a vertex v, and what you will do is first check if visited array for this particular v is already having a 1. Okay, that means a return cycle. So how can you return cycle? Maybe I'm trying to detect cycle only. So I'll say return true. Yes, I found a cycle. That this means that. Okay. Else we'll continue. Like what we said is whenever we will come here, we'll simply what we are doing is visited of v, we are marking it as 1. That okay, this is 1. Now what we were doing is for all the neighbors, let's call it all the child graph of v of that particular vertex, means it should give me, in case of 4, it should give me first 7 and then 5. Okay, likewise, it's an adjacency list, you can imagine. What we will do here is we will simply call depth first search for the child. Okay, and because it is returning, the depth first search is returning true and false. So in case you found the answer, you may need to return it from here in recursion also, right? So we'll simply check if by any chance anyone said it's true, that means if true, no need to write equals to true in Python, but normally got it. So if it is returning true, then from here also you return true. Return true, TRUE. Okay. So yeah, baseline what we were doing is we were running depth first search for every child. Once that depth first search is done for every child, that means you are done for the main node of this particular level. So visited v now becomes 2. That it's done. And you can say from here I'll return false. That I did not find any cycle, at least on this node, right? This suggests this, right? So if there is any, you can say cycle even on the sub route from this one, so you will get that answer here itself and you will return from here. Hence, you will never be able to come to this point. Hence, you will never return false. So this will be the pseudocode if you are trying to detect cycle using depth first search. Cool. So we'll use this understanding to solve some basic question first. All right, so we did this using breadth first search first, the Kahn's algorithm. Let me just remove that and try to do it with what we just learned. So we will do a depth first search on the element, say v vertex. Okay, we will simply do if my self dot visited of this particular vertex is 1 by any chance, then return true, that yes, there is a cycle. And if there is a cycle, okay, that's it. And what we said, if not, then self dot visited of this one, we are now marking it that I started doing for child in self dot g of this particular vertex. If self dot DFS means I have to self dot DFS of child, then return true, that I found cycle in a subpath somewhere. Otherwise self dot visited of this v is equals to 2, that means it's completed, and return false. Okay, so I need a one self dot visited, which I'm saying by default will contain 0 for n is number of courses. And what else? I need self dot this adjacency list, which is nothing but default dictionary in Python of list. So for every u comma v in my edges, these are nothing but edges, what I'm going to do is I'll make this adjacency list. So self dot g of u dot u, this is a directed one. Okay, so for every element in n, I'm doing it for every component like we just saw. We'll simply check if self dot visited of that particular I is 0, then do DFS, but just check if self dot DFS of I by any chance, if this is true, that means there is a cycle. If there is a cycle, then we'll say we cannot complete the course. Okay, else you do it, and in the end, if not, then we are simply saying yes, I can complete all the courses. Okay, let's just see if there is no basic errors. Looks like it is working. I see I have big cases where I made mistakes earlier, so I'll just do basic try. Yeah, so edges, which basically there are childs which already got completed, like in our case we had so basically there can be edges which got already completed, but you are again trying to solve it, that we can catch here only. If child is already completed, then no need to go into that path, it is completely visited, hence you can continue skip that one. This is the extra condition which I wrote, so I'll submit this. Rest is same what we did, and this looks fine. Okay, so this is the basic understanding that we're using depth first search. How can we detect the cycle? Now we will do a lot with the cycle and the form of the cycle. All right, let's move to the next section, which is basically finding the order itself and using DFS this time. So we will reuse exactly what we just did. So I'll go back to the code which we wrote. All right, so this is our depth first search which we did, where we were finding, if you basically found that there is a cycle, then simply return that yes, I found a cycle. Otherwise, if did not find any cycle, at least at this route, so we can say no cycle at this node or subpaths. So we can do one more thing to find the answer. Assuming I am having an answer global array, I can simply append this node into my answer. So v will be appended. So that means as soon as you will explore, so by default, if basically I do have my graph, so whichever node I will finish first in depth first search, that will be added into the answer first. So, and which is what we want here in the order, right? Which course you should take first to finish the entire list of courses. So that's the simple logic I'm using here. Same code, we just added this v. This condition we still need to check that whatever got completed. So if one course was basically dependency of two more courses. If one course was dependency of two more courses, then when we are exploring the first path, at that time itself we will be able to finish, the dependent, that child path. And when we are coming back from the other route and we'll see that that child path is already done, at that time we need not to explore that path again. So it will save us, doing that same path exploration and again and again, which is already done. So this is a very good condition to avoid the TLE. Now, this is the only change we need in our DFS to actually find the result. Now let's copy paste the same code which we did in finding whether we can complete or not. So this is n number of courses. Prerequisites is nothing but edges. That is what we did in the last one. Now what are the changes here? First, I need an answer array. So I'll define a global answer, which is nothing but an array. And finally, I just need to return this answer array, self.answer. And if there was a cycle, that means I cannot finish. Hence, I will return an empty array. That is what is asked here. That if you cannot finish, then return an empty array. So that's what I'm doing. Nothing changed. The only thing is, because I made the graph in reversed order, so it will always give me a reverse answer. Maybe let's just test it on the sample test cases. So if you see, in place of 0, 1, it gave 1, 0. In place of this, it gave the 3, 2, 1. So it is always giving the reversed order. So to fix that, I can make my graph in the given form, that U is dependent on V. Now this should be fixed. Okay, let me just submit it. Perfect. So it's done. No changes. Same DFS code which we used. States is just that when you are done with the exploration of a vertex, we just need to add it into my answer, and you will be able to find the order ultimately. The reversal which we did, let's just test here also. If I would have made the graph this way, will anything change into my answer? No. Okay, I intentionally made a reverse graph here, both ways. That dependency, that graph, at least on that all the test cases which are given here, it is working fine. Okay, and when I'm saying I did it intentionally, because now I'm going to go in, before we explore the SCC, we will also explore how graph reversal helps us solving some of the problems. But in these two questions, that reversal was not making any impact. We were able to find the same answer even when graph is reversed or graph is with the same, given edges. One more thing before we go, if I would have had it the original way, and I would have reversed the answer. Reversed this. First, let me check if this returns something. Oh yeah, the type will change if I'll use this. So I'll simply do that reversal, means read it in the reverse order, and it will give me the new list. Basically, this is a copy of the array, but in the reversed order. Let me just check. So sample test cases should pass here because the order was exactly same. But is there any test case where order was required? No. Okay. So here, these two questions, basically normal DFS with the states which we checked is working fine, and whichever node you're exploring first, appending it into your answer is basically good enough for us to find the topological order using the depth first search. Okay. Yeah, I think I'll make the next video with the next topic where we will move to graph reversal before we move into strongly connected component. Thank you.